Are we about to discover true extrasolar Earth twins? Will it help us in our quest to discover alien life out there? What is a dormant black hole? Have we discovered any yet? If we did, what can it tell us about how black holes are formed? I will tell you all about it in the very first episode of my new weekly podcast, Astro Edge.
Welcome to Astro Edge, weekly broadcast presenting highlights of leading-edge research in astronomy and astrophysics.
Here's the first paper for today, Detecting Solar System Analogs Through Joint Radial Velocity Astrometric Survey. Here are the authors. First author is Daniel Yahalomi. He is a PhD student in the Department of Astronomy at Columbia. So the second author in this paper is Ruth Angus from American Museum of Natural History. And the third but not the last author, is famous theoretical astrophysicist David Spergel. So let's have a look at the paper. So I highlighted a few important points here. What is detecting solar system analogs and why is it important? You probably heard that we've discovered lots of exoplanets, extrasolar planets, more than 5,000 at this point. But these planets are typically nothing like Earth and nothing like giant planets in the solar system like Saturn and Jupiter. Not just in terms of size or mass, but also its distance from the sun. We discover some planets which have mass similar to Earth mass, but they are much closer to the star than Earth is. Same for giant planets. We typically discover them much closer to the star than the distance in the solar system. And that matters a lot. The fact that we discover such strange solar systems, extrasolar systems, it's not because they are much more common, but because the methods, the instruments we use to detect extrasolar planets are very sensitive to this special kind of planet and totally insensitive to planets like Earth and Jupiter in the solar system. So this paper is talking about how to detect extrasolar planets which would be true analog of the Earth. Same size, same distance, similar star as in the solar system. And same for Jupiter and Saturn. The point this paper drives is to achieve this holy grail of extrasolar planet search. You cannot just use one method. You have to combine a few very different methods. And they're talking about combining so-called radial velocity method and very different astrometric method of finding planets. We're at the edge of current detection limits. So the actual Earth and Jupiter and Saturn, they are at the edge, but actually outside of the edge. They're not detectable. The methods we use right now, the telescopes we use right now, cannot discover true analogs of the Earth, of Jupiter and Saturn. This paper suggests that by combining two experiments, one is called Terra Hunting experiment. This is a fairly small telescope. I think it's around 2.5 meters on Earth. It's not a space telescope. And it will have a very special instrument called HARP S3, which can measure spectra of very bright stars. So it will focus on just very few brightest stars very close to us. And the reason they focus on nearby bright stars because that's how you can make the most accurate measurements of the spectrum. And that allows us to detect Earth-like planets orbiting nearby stars. So what kind of accuracy we're talking about? This particular experiment, Terra Hunting experiment, will measure the radial velocity of bright stars. And what is radial velocity? It's basically how fast a star moves from us or towards us. Typically, the speeds of stars in our neighborhood are like a order of 10 kilometers per second. So it's pretty high speed. And those speeds quite easily to measure. The problem is to be able to discover an Earth-like planet around a star, you have to measure its speed with a very high accuracy. And in particular, this Terra Hunting experiment, they're talking about accuracy of 0.3 meters per second, or it's like 1 foot per second. Just for comparison, a pedestrian walking is 1.5 4 meters per second. So this is like 4 times slower than pedestrian walking. And we are talking about measuring a speed of a whole sun located light years away from us with such extremely high accuracy, just mind-boggling. And even then, with this super high accuracy, we can just barely can start discovering Earth-like planets. That is still not sufficient. This paper states to discover true Earth analogs, one has to combine these kind of observations with astrometric survey. For astrometry, they're talking about Gaia space mission. Gaia is a spacecraft from European Space Agency. It was launched quite a while ago in 2013, expected to operate until 2025. At this point, it has already accurately measured positions for almost 2 billion stars. Astrometry means measuring position extremely accurately. Gaia will soon release 100 to 200 astrometric observations of the same 40 bright nearby stars, which are subject of Terra hunting experiment, observed with the accuracy of 60 micro-arc-second. This is the positional accuracy. It measures wobble in the sky. Star moves slightly up, down, left, right. And the accuracy of these measurements is 60 micro-arc-seconds. Is it a lot? To give you an idea, 60 micro-arc-seconds, this is the thickness of the human hair strand seen from the distance of 400 kilometers or 260 miles. This is the accuracy required for detecting solar system analogs around nearby stars. This is just absolutely amazing. Another point made in this paper, even though it's sufficient, just these two experiments combined, the future Terra hunting experiment, which will start operating at the end of this year, and hopefully will start producing very first discoveries of Earth-like planets by the end of the next year. But it's 10-year experiment, so one has to wait for 10 years to get the most out of it. And to combine with Gaia, which has been around for a number of years and still operating, that's what it takes to start discovering solar system analogs. But one also needs another experiment, Nancy Grace Roman Space Telescope. This is a future space mission proposed by NASA. Hopefully it will be launched in 2027. This is sort of Hubble Space Telescope, just focused on infrared light. Also, it has much larger coverage in the sky, roughly 100 times more than Hubble Space Telescope. So where Hubble has to take 100 pictures, this telescope will only have to take one single picture of the sky. So it's 100 times faster in a sense. Also can do very high accuracy astrometric measurements of stars. This paper is talking about using all three missions to first of all discover analogs of the solar system, but also to measure the mass and orbits of the planets fairly accurately. So why do we even search for solar system analogs? This is in part because we are interested in finding life around other planets. As the Earth is the only presently known habitable planet, this is what we are limited to. We just don't have a clue where else to look for signs of life. We know life exists on Earth, so first we look for Earth-like planets because we think we have higher chances finding life around other planets. So that's why solar system analog is so important. We haven't discovered yet even a single analog of solar system. Just let me show you this picture, this plot. It shows the exoplanets which we already discovered, specifically around sun-like stars. So there are almost 3,000 exoplanets. And this is a two-dimensional plot. Scientists like to plot things on plots because it helps us to visualize things. So each dot here, it's one exoplanet. Each exoplanet has its own orbital period. So it's down here. And if you go this way, it's the mass. And the scale is logarithmic. So here's 1 Earth mass. This is 10. This is 100. This is 1000. So it's a huge spread of masses, huge spread of orbital periods. So these are all exoplanets discovered around sun-like stars. And that's where the Earth is. As you can see, whatever the methods we use, they're highly sensitive to planets around here, which are roughly a few masses of Earth, but with very short orbital periods, around 10, 20, maybe 100 days. So we presently, with the technology we have, cannot discover true Earth-like planets having the same mass and the same distance from its star as the Earth. But this paper is talking about it's feasible. Within a few years, by combining a few existing or upcoming experiments, we're about to start discovering true solar system analogs. And this is really, truly exciting news. In summary, we haven't discovered true solar system analog extrasolar planets yet. But we are getting there. We are almost there. If this paper is correct, if the model they produce is correct, then within a few next years, we should be able to discover first true analogs of the solar system. And that would be super cool, because that would be a huge step towards potentially finding a life around other stars. In my book, this paper does have an edge. The second paper we'll cover today is a red giant orbiting a black hole. I'll just mention the first three authors of the paper. The first one is Kareem El-Badry. He's an astrophysicist in the Institute for Theory and Computation in the Harvard-Smithsonian Center for Astrophysics. The second author is Hans-Walter Rix, a German astronomer and director of Max Planck Institute for Astronomy in Heidelberg. The third author is Dr. Yvette Cendes, again at Harvard-Smithsonian Center for Astrophysics in Cambridge. So there are two important keywords in the title of the paper. A red giant, it's a star orbiting a black hole. A red giant star is what will eventually become the Sun. 4 billion years from now, our own Sun will turn into a red giant star. So red giant stars are very bright, much brighter than Sun is currently. Can be less massive than Sun, can be up to 8 times more massive than Sun. And this is the dying stage of stars of this mass. At the end of their lifetime, stars run out of hydrogen, which is the main fuel in their cores. Hydrogen fuels most of stars in the universe. Once star runs out of hydrogen in its core, it will continue burning hydrogen in the shell surrounding the core. But that changes structure of the star. It becomes extremely bloated, dozens of times larger than Sun. It becomes a bit colder, that's why it's red rather than yellow as Sun is, and becomes super bright because it is so bloated, so large. What about black holes? Everyone heard about them. These are enigmatic objects which are very massive, many times mass of Sun, extremely small and dense. They're so small and so dense and so massive that nothing, even light, can escape a black hole. Anything goes in, stays there. So far, we discovered most of black holes indirectly by detecting the gravity pull from black hole on nearby stars. Also, sometimes we see black holes which are surrounded by gas, interstellar gas, and if there is enough of that gas, the gas starts shining, glowing. So we can detect black holes from that. And very recently, we made first direct detection of black holes, as you can see in this image. At the center of galaxy Messier 87, there is a massive black hole. Using special radio telescope, we managed to see both the super bright gas surrounding the black hole, and we see the shadow from the black hole. So this black hole is gobbling up the gas surrounding it. So we see both the gas, but for the first time, now I think we have two examples of that kind. We see actual shadow directly from the black hole. This paper discusses a particular interesting situation when there is a black hole orbiting around red giant star. In fact, they both orbit each other. Their masses is not that much different. So they make a binary. This star was observed earlier by the Astrometric space mission Gaia, which we discussed earlier. And from these observations, astronomers discovered that some stars are moving slightly back and forth in the sky. And by careful analysis, they came up with two candidates. They see two stars which move in a way that can only be explained if they have an invisible black hole companion. And these candidates were called BH1 and BH2. So the BH1 was eventually confirmed to be actually true black hole orbiting or making a binary with a visible star. This particular paper talks about the second candidate, BH2. So what did these researchers do? They used a bunch of different telescopes. They used visible optical telescope, they used ultraviolet telescope, radio and X-ray telescopes to pretty much rule out any other explanation for that wobbling of the BH2 candidate. They use techniques of spectroscopy, measuring spectra, and also use photometry, extremely accurate, precise measuring of the brightness of the star. They put it all together and they basically eliminated any other possibilities for the wobbling of the BH2 star. All kind of normal objects or semi-normal like white dwarfs, neutron stars, regular stars, they would all show up in their observations, but they didn't. Whatever wobbles, moves the BH2 star is completely invisible in the analysis. By putting all this together, they estimated that the mass of the invisible companion, which they believe to be a black hole, is around 9 masses of Sun, so 9 times more than Sun. These two objects, the red giant star and black hole, orbit each other with fairly long period, 1200 days. This is much longer than any previously studied black hole binary. This is one of the things which makes this research unique and this discovery unique. They use radial velocity observations. Remember, we discussed radial velocity. This is the speed of an object moving towards us or away from us, and you can measure that by doing spectroscopy over a 6 months period. And they use that to complement what Gaia space mission did to figure out all these parameters. They also figure out that this star or this binary object moves in a thin disk of the Milky Way and is a part of thin disk of the Milky Way galaxy. Here's our own Milky Way galaxy seen edge on from its edge. So the thin disk is the blue line in the middle. Here's the center of galaxy, which has large black hole. The sun is located here, and the BH2 object is located somewhere here in this blue area. What is very important is discovered that this is only the second case when we discovered dormant black hole binary. Most of black holes we discovered so far, we can see them because they're so close to their companion star that they radiate a lot of energy in X-rays, so they become quite bright in X-rays. But objects like BH1 and BH2, they're very special, the first of these kind of dormant black holes. In fact, researchers calculated there should be many more dormant black holes, binaries, in our galaxy compared to the ones we discovered so far to be X-ray bright. This is a tip of the iceberg, so there are many more discoveries of these very enigmatic objects, dormant black holes, to come. In terms of distance, it is fairly close to us. It's further away than BH1, but BH2 is a bit more than 1 kiloparsec away, which is around 4,000 light years. Still pretty close by Milky Way standards. Milky Way size is around 100,000 light years. These researchers used a few different telescopes. They used optical and ultraviolet telescopes, but they also used X-ray telescope and radio telescope. They did not detect this object at all in X-ray and radio waves. That was one of the important factors which led them to conclude what we're dealing with is not a regular star, but in fact a dormant black hole. So what kind of telescopes they use for their research? For visible light, there is a fairly small telescope in La Silla Observatory in Chile. For ultraviolet observations, they use very large telescope, which is 8-meter diameter telescope, also in Chile. And they also used Space X-ray Observatory Chandra and radio telescope Meerkat, located in South Africa. Here's the optical image of this star. So the bright star at the center is BH2. Its visible magnitude is around 12, which is very bright. You can actually see with a fairly small amateur telescope, like 8-inch telescope with good skies. And then the researchers speculate, how could such a pair of objects form a red giant star and a black hole. All the black holes of this mass, the few solar masses, they are believed to form after a very massive star, O stars, which live very short lives, around 10 million years. For comparison, Sun would live around 10 billion years. They die in a giant bang called supernova explosion, and often, maybe always, what is left behind is a remnant called black hole. If these two objects were born together initially, the star which would become now red giant star and the progenitor of the black hole, these researchers are saying that the progenitor of the black hole should have been very, very massive. One of the most massive stars in the universe, more than 65 times more massive than Sun. Alternatively, it could have been a less massive O star, which gave birth to black holes, but black hole should have formed by itself. And then while wandering through the Milky Way galaxy, it just accidentally ran into the star which became red giant star and captured it. In conclusion, thanks to the Astrometric space mission Gaia, we starting to discover very interesting exotic objects, such as these dormant black holes. This is just the tip of the iceberg. So far, we discovered and confirmed two of such objects, but there are many, many more to be discovered. Very exciting research, very interesting prospects. As far as I'm concerned, this research does have an edge. This is just an experiment. I'm still trying to figure out if I can have enough time to run this weekly. Please, if you're interested, let me know. Put a comment down below. And I would really appreciate if you subscribe to my channel and give me a thumbs up. See you next time.